Okay, so let's get started. We have to end by 10:10 today because there's another class here. So I will start on time. So I'm going to finish the last few slides on distributed communication, and then today we will start a new topic which is on naming. Okay? So if you remember, last time I was talking about audio and video streaming as a different way for to have distributed communication between clients and servers. And towards the end of the class, I was talking about HTTP streaming. Okay, so if you look at most of the video streaming over the internet today, it uses HTTP. Okay, HTTP is a protocol that was designed for requesting web pages and images and getting responses. It was not originally designed for something like streaming. It is a request response protocol. Okay? Nevertheless, it has been adapted to support audio and video streaming. Okay? I had said that streaming uses typically a server push architecture where you just press play and then the server starts streaming data to you. Okay? Now that's not possible if you use HTTP, because HTTP is fundamentally a client pull protocol. It's a request response protocol. So what happens in HTTP streaming is you take your video file, okay, and you partition it into smaller chunks of few seconds of video each. Okay, so your entire video file is split into smaller files which have few seconds of video each. And then what your player is going to do is it is going to send explicit requests for each of those files. And while one file is playing, you may have requested several files in the future just so that you can buffer enough data. Okay? That's one. The second thing that HTTP streaming will do is it allows you to deal with losses or late arrivals by actually modifying the quality of the video playback in real time. So each video file is encoded at different resolutions or different quality. Okay, resolution says what's the screen size, what's the pixel resolution, which is specific to certain screen sizes, and the quality also says what is the bit rate at which you encode. So you might have standard definition, high definition quality, and so on. So in this case, you'll see that there are three resolutions: 128 kilobits per second video, 256 kbps, and 512 kbps. And you might have more than three qualities. If you want HD quality, you have to go in megabits per second. Okay, so you will have these different quality levels. And what your player will do is it will look at how the network is behaving at any given time. If data is not arriving at a steady rate, when you request the next chunk, you will actually drop in quality and say, let me get a lower resolution version just so that I do not see playback glitches. Because the more you try to retrieve and the more congested the network, more problems you are going to see. So you might actually start with the base level. If the quality is good, you might keep making the quality of the video better. The network bandwidth is available and it's not congested. And if you start seeing problems, you might temporarily drop the quality and then raise it and so on. Yeah, this is why when you use YouTube players and so on, sometimes your video starts appearing grainy. The reason is your video player has dropped the quality just because there may be some network problems it is observing in real time. Okay? And then once those problems go away, the quality improves again. Okay? That's the trade-off you make over just keeping the quality the same but then having playback glitches because data did not arrive on time. Instead, you try to get less data on time rather than not get data at all. Okay? So all of this HTTP streaming protocols are actually referred to DASH protocols. Okay? Direct adaptive streaming over HTTP. Okay? That acronym DASH is essentially a way HTTP is used for streaming purposes. Okay? So now the flip side of this or another issue here is HTTP runs over TCP. Okay? Many early UDP streaming protocols use the UDP protocol. Okay? But HTTP uses TCP, but you can get around TCP retransmissions taking longer times and so on just by improving the buffering capabilities at the client. Okay, so that's something to keep in mind that despite UDP being a better product transport protocol for meeting timeliness constraints and so on, by far all of the streaming that happens over the internet, whether you're doing YouTube or Netflix or any of these streaming services, they essentially use this kind of protocol, which is HTTP or TCP. Okay, the last point I want to make in this set of slides before talking about naming is stream synchronization. Okay, so if you take any video stream, typically it will have multiple substreams encoded in it. Every video file will at least have a video stream and an audio stream. Okay, the audio is the audio data that goes with the video data. Okay, so you will essentially have at least two streams, many times more than two streams. Even audio streams may be split. If it's stereo audio, you might actually have multiple audio channels so that you can play on your left speaker and right speaker and so on. Okay? Now what happens is when the data arrives at the machine, okay, the machine has to split these streams, okay, and the video stream is displayed on the screen, and then the audio stream is played out on the speaker. Okay, so you have to essentially play out different streams on different hardware devices. Okay? And in order to ensure good quality, you need what is called stream synchronization. Okay? And essentially, when you're playing a video file and some video images are being shown, the speaker needs to actually play out the audio that goes with that video. Okay? So if you do not have stream synchronization, you will lose what is called lip sync. Okay? Lip sync says when you see the person's lips moving in a video image, you want the same audio to be played out, otherwise you will see a problem. Okay, you will go out of lip sync. Okay, so to ensure lip sync, you want to ensure stream synchronization. And this is not easy because I have a picture, I think, here. So you will see that both the capture and the playback actually happens through independent devices. So when you, let's say you're doing video conferencing or Skype or Google Hangouts, okay, your video is captured by the camera, okay, and audio is actually captured by the microphone. Okay, there are two independent devices. Okay, and then your audio stream is generated by the microphone, the video stream is generated by the camera. Okay, and then you have to then timestamp both of that streams so that you know when each audio sample or each video file needs to be played out. Okay, so the way synchronization is going to be achieved is through timestamping each of the substreams, and you need to ensure that you timestamp it carefully so that at the playback end, when you're playing an image, you need to know what is the corresponding audio data that has to be played out. Okay, so we will talk about synchronizations 2 classes from now. Okay, and then at that point, we will see how you can synchronize various things and so on. But what you need to understand is underneath audio capture and video playback is a synchronization mechanism that takes all of these substreams and then inserts timestamps and uses the timestamps for good quality playback. Okay, so that's something that's important as well. Okay, so I'm going to stop here and see if actually I have one more slide, but let me pause to see if there are any questions on audio and video playback. Okay, so the very last slide on this topic is on multicasting. Okay, so if you remember what I said maybe last time or 2 classes ago, I said that in many cases, most communication involves 2 entities, a sender and a receiver, a client and a server. But in many cases, communication could also be group communication. You send once and then that data is received by multiple entities. Okay, so this could be used using what are called multicast protocol. Multicast is a form of limited broadcast where you're sending the data. Okay, you do one send, but you address it to a group and there are multiple recipients in it. Okay, so if you have excuse me, a popular, let's say, sports events that are being streamed live on the internet, that's typically what they call it a webcast, but essentially it's a multicast mechanism where lots and lots of users are tuned in and the server is sending one stream out and it is being delivered to tens, hundreds, potentially sometimes millions of users. Okay. And this multicasting protocols require that you essentially have what is called a multicast distribution tree. Okay. The root of the tree is the sender, and then data is sent over this multicast tree. It propagates through the multicast tree, and each of the leaf nodes in this multicast tree is one receiver, is one person who is tuned into that webcast. Okay, so any multicast framework will require you to construct this multicast tree. If you are using native IP multicast, which is a multicast protocol supported at the IP level, then this tree is also handled by routers and so on. Okay? But in many cases, you can use application level multicast where you have what are called overlay nodes that essentially construct this tree and they overlay it onto the network. Just as a P2P network is an overlay network where the P2P topology is independent of the underlying network topology, so can an application multicast tree be also an overlay network where the tree topology for the multicast is independent of the underlying network topology. Okay, so parent and child don't have to be adjacent nodes in the network sense. Okay, they're just arbitrary nodes in the overlay network. Okay, so that's something to keep in mind. I won't go a lot into details of multicasting and whatnot. That's topic for a graduate level networking class. But all we need to know from our perspective is it is a form of distributed communication where you have one sender, multiple receivers. Yeah, and this is something that we might have to use in various different contexts for the labs and so on. Any questions on this before I move on to naming?
So,
yes?
is there a standardized protocol for multicast, or is it like a mechanism to send to multiple agents?
Okay, question is there a standardized protocol or technique for multicast? So there are standardized protocols. As I said, there is something called IP multicast. Okay, so you can actually use TCP/IP to do multicast. Okay, this requires that you turn on multicast feature in your network routers. Okay, default router may not have that feature turned on, but it is a protocol. It is something that native TCP/IP will support if you have turned on multicasting first. Yeah, but that requires network level support, which may not always be available. In that case, you implement application level protocols, and there are many different ones. There's middleware that you can get that also does it. Yeah, so there's not one standard protocol for application level multicasting. There are many.
But in a network, isn't multicast just one IP address where if you send something, it goes to everyone in the subnet or the network?
Okay, the question is, if you do IP multicast, isn't it one address where you send to one address and receive it? If you use IP multicast, the abstraction of send is the same as sending on a socket where there's only one destination. So rather than creating a unicast socket, you construct a multicast socket and a multicast address. So all the receivers actually listen on to that address. Okay, so from sending perspective, you just do one send. So you are at the root of the tree, you just send once. The network has constructed an IP multicast tree, and a packet will propagate and be duplicated along the paths of the tree and will reach the leaf nodes, which are all doing a receive. So you still use the socket abstraction if you are using IP multicast. Okay. Okay, so let me switch gears a little bit and move on to the next chapter. Okay, this is going to be a short topic. Okay, it's going to be on naming. Okay, so and specifically on distributed naming. Okay, so let me explain what we mean by naming, and then we will see how to go about it. Okay, so essentially, all resources in any distributed system or applications are given names. Okay? And other entities in your system can address these resources using names. Okay? And there has to be something that maps the name of a resource to the underlying entity of the resource. Okay? And then to do this, you are going to need a naming service. Okay? Now, you may have already encountered this in your lab. If you are using RPCs or RMIs, you register the server to a naming service. Okay, the server has a name associated with it. When the client needs to bind to the server, it has to do a name lookup. Okay, and basically the name lookup allows you to specify or address the server by name, and it maps it to, in this case, the IP address and the port number where the server is listening. Okay? And this is just one example of many where naming comes into play. Okay, and what I'll talk about today is the domain name system, or DNS, as an example of a distributed naming system. Okay, if you have a very large distributed system, the number of names that you have in the system itself will be large. Okay, so you cannot have one name server that's going to handle all your naming requests, and your naming system itself has to be distributed in nature. Okay, so what we are interested in here today is how to construct large distributed naming systems, and we will use DNS as a case study or an example of such a system and see how to construct them. Okay, so that's essentially the concept of naming, and for the most of this class we will actually use machine names to IP address mappings as an example of what kinds of names we need to resolve. But you should keep in mind that you will have arbitrary names in any distributed system, and the same concepts apply. Okay, so for as an example, what we are going to look at is what happens when you type www.cnn.com into your browser. Okay, your browser is going to do a name lookup to DNS. Okay, DNS will actually map that name to the IP address of the machine. Okay, the user does not need to know any of that. You just need to know the name of the server, which in this case is a URL. Okay, the names here are URLs, and DNS maps these URLs to IP addresses. Okay, so that's going to use name resolution. Okay, so let me now talk about two canonical approaches for distributed naming. Okay, so when you have lots of names or lots of entities that have names and are performing naming lookups, your distributed naming system is going to be distributed in nature. Okay, and the way you are going to construct a distributed naming system is through one of two mechanisms. Either you are going to use a hierarchical structure where your names will be hierarchical in nature and your naming system will be hierarchical. Okay, or you are going to use something like a distributed hash table or DHT and a P2P like name lookup to actually look up names. Okay, so you already encountered this when we talked about CORD. Okay, CORD is a distributed hash table or a DHT, and you do a key value lookup. Okay, in this case, the keys are the names and the value is what the names map to. So the same concept can be used in a naming system as well. Okay, but I will not talk about P2P name-based lookups today. We will only focus on hierarchical name. Okay, but you should keep in mind that there is a class of naming systems that also uses P2P concepts to implement naming. Okay, distributed naming systems. Okay, so let me start with very simple example. Okay, so you have to do name lookups in many different contexts. A very simple example is essentially file names. Okay, so when you open a file, you specify a name of the file in your program. You might say open and specify a file name. Okay. Now underneath, your operating system has to take that file name and map it to an internal name. Okay. The file system does not actually use file names to organize files. It actually uses IDs, which could be integers typically. Okay. So internally, every file name has a unique ID. Okay. But for human ease of human understanding, you do not address names by their internal IDs. You specify a name with it. So you will say lab1.java because that's easy to understand rather than file 523. Okay, that you will not be able to figure out that if you only files had only IDs or numbers as opposed to names, that would be much harder. Okay, so what file systems do is the abstraction provided to users allows you to associate names. But internally, when you specify a name and you try to address a file or open a file, you have to map it to its underlying ID. And that is what is actually done through a naming-based system. Okay, all file systems also implement simple naming. Right? The file system namespace typically is hierarchical. So you have a concept of a root directory and then subdirectories and subdirectories and so on. And leaf nodes are essentially files. Okay? Intermediate nodes are in your file system hierarchy are going to be subdirectories and directories. So if you want to then resolve, let's say /home/team/mailbox, okay, which is where this user presumably receives mail, you have to do a recursive lookup through a hierarchical lookup through the file system namespace. So you're going to start at a root directory / and then say, is there a subdirectory called home and /? So you're going to search the root directory, look for a directory called home, which you do find in this case. Okay, there will be many different directories or subdirectories there. So you look that up. Then you will open that subdirectory home, and then you will do the next level lookup, saying, is there another directory called Steam in there? So you will look at all the entities in the directory home and look for Steam. Okay, so you are basically descending down this hierarchy. And then once you find Steam, you will open that directory and say, is there a file called mailbox in there or mbox in there, which you find. And then you say, okay, I found the file, now what is the internal ID of the file? You'll find that internal ID, then you open the file. Okay? So whenever you touch any file on your machine, your OS has to perform these operations. It will start at the root, it will do a recursive set of lookups until it actually gets to the underlying. You're going to do hierarchical name resolution. So this simple example just tells you what name resolution looks like. You take each component of the name, so you look at slash, home, steen, mbox, so those are all components of your file name. And then you're doing individual lookups on each of those and until you find the right resource you're looking for. The same concept will apply in any naming system. Okay, your names will have hierarchical components and you are going to actually look at each of those components and try to find the resource the user is trying to address or the application is trying to address. Okay, yes, question?
So in case of symlinks, can you please explain how it will work? Like if a symlink is actually, if the file is actually in another directory, and if accessing a symlink in the other directory, so does it have to recurse back and then go back from the one?
Okay, the question is if you have symbolic links, how are names resolved? Okay, and we'll come to that also when we talk about distributed file systems, but let me give a very quick example. So there are file systems actually support two kinds of links. There are hard links and soft links. So both of these are aliases for files. Okay, typically a file can have multiple names. Okay, most of the time a file has only one name. Okay. When you create a sim link or a hard link or a soft link, you're associating a second name to a file, and a file can actually have more than one name. And you can address the file through any of those names and it opens the same underlying file. Okay? So essentially symlinks are aliases for files. You can have more than one alias. They all map to the same file. And that's first of all what hard links and soft links are. Now as far as resolving it is concerned, you're going to essentially have the same mechanism. Okay, so essentially your link will point you to the same file. If it's a hard link, then both of those will essentially point to the same file, which means this is going to be a directed acyclic graph. It's a DAG, not a tree. The reason the file system hierarchy is a DAG is you can associate N3 to be another name for this file, and then they'll both point to the same file, and now this tree has become a DAG. Okay, so essentially this is the whole reason why your file system hierarchy is a DAG. But be that as it may, if you have hard links, you'll just descend down the hierarchy and you'll just land up at the same file because it'll point to the same file. If you have soft links, which are also called shortcuts in Windows, if you use shortcuts or aliases, then essentially a file is a pointer to another file. It's not pointing to the file, but it's a symbolic, you think of it as a pointer. So when you resolve it, you will actually find a pointer saying if you want to open this file, open this other file instead, and you will be given a different name. In that case, you take that name and you re-resolve it, and then you'll find the file you're looking for. So that is how you're going to do name resolution when you have aliases in your file system names. Any other questions on this? Because, but that was just an example. I'm going to also show you now how you can do this in a distributed fashion. Okay, this was essentially how you resolve name and all the files reside on your machine. Okay? Now, if you have a distributed file system, some of the files may actually reside on the server, not on the client. And then your name resolution has to become distributed. Okay, so let's take an example where you have machine A, which is a client, machine B is a file server. You have taken some files or a directory from the file server and you have mapped it onto the client, okay, using a protocol. In case of NFS, this is called the mount protocol. Mount protocol simply establishes a mapping of a local directory to a remote directory. Okay? So when you then open this local directory, okay, essentially you are seeing files that are on a remote directory because you just constructed a mapping using the mount protocol. Okay? So in this case, what is going to happen is if you are actually now looking for that file, you will descend down the hierarchy, you will hit a mount point, which the OS knows about explicitly. So the OS knows anything that is now underneath this directory is actually files that are in a remote directory. Okay, and then it will say, I did partial name resolution, let me now send the request off to the server and ask it to resolve the rest of the name. Okay, because the file actually resides on the server, so you are going to do partial name resolution locally, figure out that you are trying to access a remote file in a distributed file system, send the file name off to the server saying, why don't you resolve it and give me a handle to the file. Okay, so in this case, what we have generalized from the previous case is part of the name resolution, okay, is done at the client. Okay, so you start at the root and you get to some point, then you say this is now a remote file because this is a mount point, and then you go send that off to the server, and then you will actually go down the path and find the right file then. Okay, so name resolution in this case involves multiple entities. This is why it has now become distributed. These are just simple examples of how we are going to generalize it to real naming systems. Okay, yes, question.
So it's actually not the OS that is doing the remote request, right? The NFS client will do that. The OS still sees it as some files on its own file system, but
So
the
the-
NFS client actually does
So the
the.
question is the OS doing it or the NFS client is doing it? You have to, the answer is NFS client is essentially a module inside the OS kernel, not a separate entity. So the NFS client is part of the OS kernel code. So when I say OS, indeed it is the NFS client. So first thing you have to realize is when you start off, it's the OS file system naming lookup that's going to be doing this. When it hits a mount point, you then say this is now a remote file. So you hand it to whatever module inside the OS is actually going to handle that. In this case, if it's NFS mount, it will be NFS client. That's still part of the OS. So that is going to then do an RPC to the server and ask the NFS server code on the OS at the server side to do the rest of the lookup. Okay. So yes, technically it is the NFS client and the NFS server, but they are part of the OS in this case.
But when you finally want to open the file, will you make a local copy on your machine?
Okay, so question is when you open the file, will you make a local copy? When we come to distributed file system, we will see there are many different ways, because this is just name resolution. We are not talking about how to design the file system itself. So the question you asked relates to how can you actually open the file and provide read and write access to. That's not the topic here. We are just trying to figure out how to map names to files. Okay? But to answer your question, either you can make a local copy and then provide local access, or all read-write requests can be sent off as remote requests to the server. Those are the two modes in which file systems can be built. But we'll come back to that later, and not for today. Okay, so that's mount protocol. I wanted to show you quickly how mounting works. So I'm going to use a GUI-based mount. So here is an application that will allow me to mount a files on the file server. Okay, so now what you have done is I have mounted a directory from a server onto my machine, and all these files that are just showing up as local files are actually remote files. Okay? If I try to open a subdirectory here or try to open a file here, you will do a name resolution, and then the rest of the name resolution will be sent off to the server, because those files, although they look local, are actually all remote files. They are not on this machine, they are on the server, but they appear to be local files for ease of users' convenience. Okay, so in this case, name resolution, so now that we have just done a mount here, okay, the name resolution from this point on for this directories and every file in it will be split between my machine and the server where these files reside. Okay, so that's just an example of how mounting works. Okay, so with that background, let's now look at some canonical distributed naming system. Okay, so naming in large systems may be global in scope. Okay, if you look at the internet, okay, the naming system actually involves millions or tens of millions of machines or more. Okay, in fact, if you now start adding phones as also devices on the internet, you will have billions of nodes in your internet. Each of them needs a naming service, and they may themselves be part of the namespace. Okay, so the naming system has to scale to potentially billions of devices in very large scale distributed system, and internet is an example, one such example. So in this case, the naming system will be highly distributed. You will not have one name server that's resolving everything. It will be handled by a large collections of servers that collectively provide you a naming service. Okay, in the case of the internet, we have the domain name system, or the DNS, that is going to provide us a service which maps names to IP addresses. And the way all of these namespaces are handled is you will essentially have a hierarchical mapping. You will have at the top layer is called a global layer. This is the root of your name hierarchy. Okay. And then the next layer is going to be an administrative layer, which are essentially individual organizations. And the lowest layers are essentially what are called managerial layer or real nodes. Okay. I'm going to illustrate this with a picture of the DNS hierarchy. Okay. So essentially the top level of your DNS hierarchy are top level domains. Okay. You will have .com and .edu and .gov and one for each country, and now there are hundreds of these domains. They are all top level domains. Okay. That's the global layer in the DNS. It changes rarely. Only when a new top level domain is added, which might happen every few years, will you actually have new nodes appearing there. Okay, but it's mostly static. That's the highest level of your hierarchy. The administrative layer is essentially the organizations that are part of each of those domains. Okay, if you have, let's say, CNN.com, CNN is part of the organization layer. Or if you have umass.edu, UMass is the organizational domain, edu is the global part of the global layer. Okay, so then you might have each domain have subdomains. Okay, you have cs.umass.edu. CS is now a subdomain within the UMass domain. Okay, so that is when we start getting down to the managerial layer and so on. And all the leaf nodes here, which are not shown, okay, are essentially machines in the DNS. So if you are www.cs.umass.edu, www refers to the web server in this domain. Right? That's a specific machine. Okay, so those will all be part of the managerial layer. So there will be most frequent changes at the lower levels of the hierarchy. Machines will come and go. You might reassign IP addresses to machine, you might replace machine, bring in new machines and so on. Okay, so as you go up the hierarchy, changes become less and less frequent. Okay? Top level domains change rarely. Okay, the next level you might register new domains or deactivate existing domains. So there will be changes, but not that frequent. But at the bottom you will see the most changes. Okay? So now there is some implication of why I'm even saying this. So the frequency of changes will have something to do with how we do name resolution. Okay. Any questions on this? I presume you all at least know what a DNS name looks like. This is just a picture that depicts it. Okay, so this slide illustrates some of the requirements at different domains in terms of how many nodes are there, how frequent changes you have and so on. So you will see at the top global level there are few nodes, administrative or specific domains there are lots, and managerial will be really vast numbers. As far as responsive to lookups are concerned, we will see that as you go down the hierarchy you need faster lookups, because we will use caching to actually reduce the load on higher level domains. So you can afford to be a little bit less responsive as you go up higher. Okay? And then as far as when you make changes to the domain name system, okay, you want to also see how quickly those changes are visible. Okay? Typically, when you make a DNS change, it may take anywhere from 2 hours to 24 hours for the change to be visible. Okay? Because you will make a change in one DNS server and it will slowly propagate those changes. And because data may be cached, okay, the changes may not be immediately visible. Okay? Having said that, because there are more changes down the stack in the hierarchy, you want those changes to be visible more quickly. Okay? And the way you are going to do this is you are going to cache that data for smaller periods of time, let it expire faster. Okay? And so on. So then we'll talk about caching as well. Okay, so now let me talk a little bit about the DNS specifically, just to give you some idea of how the DNS system works. So think of DNS as essentially a very large distributed database that does key value lookups. The key are machine names. The values are IP addresses. Okay? And this the DNS system has different kinds of records in this database. And this table shows you different kinds of records. The most common one is called an A record. Okay, an A record is an address record which basically takes a name and gives you the IP address. Okay, so that's an A record. You can have something called an MX record, which tells you for that machine what is the mail server responsible for receiving email for that machine. Okay, so that's called an MX record. You can have an NS record which says what is the local name server associated with a given domain, because it's distributed. Okay, and you look at CNAME record. Okay, CNAME records are aliases. Okay, just as a file can have multiple names, a machine can have multiple names as well. Okay, so you can associate multiple names with a machine. So every machine will have one A record, which is its actual name, and it can have a set of aliases. Okay, the aliases are actually encoded using CNAME records. So you look up a CNAME record, and the CNAME record may then point to an A record and so on. And then there are some other kinds of records which may not be as important. Okay. So these are all kinds of records you can actually see in a DNS system. Let me actually show you an example. you can actually go and do your own lookups should you want to. So you can basically use the host command or an ns lookup command to figure this out. Okay, so I'm going to just do www.cs.unix.edu. Okay, so you will see, so that's basically, if you do that, it tells you the IP address. Okay, I'm going to make that bigger. Let me do an ns lookup, which is easier to understand. Okay, so if you actually do our GOS, so this is going to basically allow you to take the address and map it to a specific, the name and map it to a specific address. Okay, and then you can then figure out what kinds of records they are and so on by, I'm going to show you another example. Okay, so if you actually look at the machine that hosts the website for the course, you will see that that machine is essentially an alias. So that's a C name for another machine, which is the actual. And then you will see if you do a lookup for that, you will say this is an alias for the other machine, that other machine has this IP address. And you'll also see there's an MX record here which says this mail for this machine is handled by this other mail server instead. So you see that this is returned as three records, a C name record, which is the alias, the A record, which is the actual name and IP address, and an MX record, which says this is essentially the mail server for this domain. Okay, so when you do any form of DNS lookup, you will actually get this kind of information back from your DNS system. Okay, so now let's take a look at how you do name resolution in a DNS system. Okay, so here we have to resolve the following name, ftp.cs.vu.nm. Okay, so presumably that's the FTP server in the computer science department at this university, okay, which is the university of the authors of the textbook in Netherlands. Okay, and then there's a domain name, top level domain name for Netherlands. Okay, so if you type this name, okay, question is how do you arrive at the IP address? And the way you are going to do this is you are going to then do hierarchical name resolution. You are going to start at the top, country level domain, and say, well, first you are going to start at the root and say where is the domain name server for the top level domain, and then it's a country level domain, you will get that domain. Okay? So then essentially that's the root name server. Okay, that's going to tell you the domain names, the server that handles all requests for Netherlands. And then you will send the rest of the name saying, I want to resolve VUCSFTP, you will basically send it to the next level. Okay, and then it will say, if you want to resolve that name, go ask the domain name server for the university instead, and you will get the name server for that university. Okay? And then you basically send this name off to the university, and it will say, you have a machine with this name, and that might say, go and ask the domain name server for the computer science department. Okay, so then you iteratively go there, and then you ask, saying, do you have machine FTP? And it will say yes, and then give you the IP address. Okay. So you've taken a domain name, to partition it into pieces, so starting with the root domain all the way to the machine name, and you've iteratively gone and looked for the domain name servers for each of those levels of the hierarchy until you reach the bottom one, which will give you the IP address. Okay. This is called iterative name resolution. We are iterating, looking for the name by descending down the hierarchy. Same thing that happened in the file system case. You know, we are seeing this happen in the DNS case. Okay? So that's one way to do it, and here is the actual hierarchy that is actually descended down. Okay? And each of this is a name server for that level in the hierarchy. Okay, here is a different way to do it, which is called recursive. Okay? The recursive case, you just give the name to the root domain server and say, you go find it and give me a response. I'm not going to keep on iterating. Okay? So in this case, what will happen is the name resolution request arrives at the root name server. It figures out what the next name server, it will forward that request down the tree. So the request will trickle down the tree, going down to domain name servers at each level until you find the machine, and then the responses trickle up the tree, and then the response comes back from the root name server. Okay. This is called recursive lookup. Both will give you the same end result, but there are two different ways of resolving a name. Okay. And we'll see that there are some pros and cons of doing it in either way. Okay? So what you can see in this case is, from a client's perspective, you only made one request and got no response. Okay? But if you think about this, every request for DNS lookup is starting at the root of the DNS system. Web pages they look up, or how many machines they connect to, you will realize that all of those requests for name resolution will actually go to the root servers of the DNS system. Okay? Now you can imagine the load that is going to get imposed on the root machine. If every lookup from all the billions of users that are using phones or devices are now all going to start showing up at the root name server, it will tremendously increase the load on the server. Okay? So that's a downside of doing recursive. Now, client's perspective is advantageous because you're only sending one request. Okay? And if it so happens that all these machines are actually in some other continent, then the number of cross-continental hops is reduced. Okay? So I have another picture here that shows you what happens in both iterative and recursive. So if you're iterative, let's say your client browser that is trying to access that machine is in North America, all of those servers are actually in Europe. Okay? If you're doing iterative, every time you decide on the hierarchy, you're sending a request that actually goes over a transcontinental link, it comes back. Then you send another request for a transcontinental link, it comes back. So your round trip times for each of these requests is going to be large in iterative name resolution. Okay? In recursive, you only send one request. It arrives at the name server, and then all of those are local within that country, so the subsequent hops are much smaller. Okay, so presumably ignoring the load issue, if you have long distance between the client and the name servers, recursive should be better from a performance standpoint. Okay. In iterative, you will have longer RTTs. But from the infrastructure standpoint, in the recursive case, the load is much higher up the hierarchy. Okay, so your machines have to be more powerful or handle very large amounts of requests, which is not the case in iterative, because you might say, why would that not be true in iterative? Am I not starting at the root of the tree every time I do that anyway? As the root name server. Okay? The reason you will not have the same amount of load in iterative is because you can actually cache previous requests that have been resolved at your local machine or the local name server. And so, for example, you don't have to go to the .com name server every time. If any user in your organization has resolved it, you can actually cache the results of that server. So you don't have to go to the root and say who's .com. Or if someone else has gone to CNN, you can actually cache those results and not even have to go back. Okay. So by having caching at the client, you can substantially reduce the overhead of iterative name resolution and only just start at the level of the hierarchy from where you have to do further resolution. Okay, so caching can substantially reduce the overheads required in name resolution.
Why can't caching help in the recursive part?
Okay, question is, why can't caching help in the recursive part? You will use caching in the recursive part, but you will have to do this within the name hierarchy, because you're always sending the name server request
No,
here.
why can't we cache the subdomain so that client actually requests the subdomain directly?
Question is, why can't you get the subdomain? You are never actually, you are only sending a request and getting an IP address. That you can cache. But if you have, let's say, gone to vu.nl previously, partial results are not seen by the server. They are only seen within the hierarchy. So they can only be cached in the hierarchy. So instead of CS, if next time you want to go to ECE, you still have to send that request down. In the iterative case, you will actually just start from here because you already know those results and descend down from there. Okay? So there are some differences in what you can cache and where you can cache.
So when you say root name server, you mean the dedicated server in a particular LAN which is hosting the name service, right?
The root name server is the root of the domain name hierarchy. Every organization has a local name server. So in this case, although I said the client is making the request, that is not strictly true. Okay, the client is in some LAN and there's a local DNS server in the LAN. So whatever the browser always sends the request to the local name server. So this is really the local name server in the client organization that's doing the recursive and iterative. Okay? The browser itself doesn't do that. It will send it off to the local name server. Any other questions? Okay. So you have iterative versus recursive, and these principles apply regardless of which hierarchical naming system you use. It's not specific to DNS. So you have these two mechanisms. There are some pros and cons depending on what you can do with it. Okay, so here is some records of the kinds I was telling you about. So these are just entries within a domain name system, and you will see there are different kinds of entries. That's the CS, VUNL. You will see there are mail servers, which are MX records within that domain. Here are some A records that actually point to machines. Here are some aliases. You'll see www, which is the web server for that department, is actually an alias for another machine. Okay? And then you'll see that machine has its own record, which will give you the IP address and so on. Okay? So these are just a set of example entries that show you all the various kinds of things you can do. And you will see Hinfo tells you what kind of a machine it is. So that's a Unix machine and so on. Okay, yes,
So
question.
which of these two approaches are used in the World Wide Web generally?
Okay, which of the two approaches are used in the World Wide Web? So it's not just the web, it's any TCP/IP based lookup. So typically you will use iterative, not recursive, in the DNS case because that just doesn't scale. Okay, so you are
So
essentially
the client would be doing multiple calls.
yes, so the client's name server
Name
is
server.
going to be doing multiple calls, and this is where I think the caching is also going to help. Okay, so one thing I forgot to mention is you will actually, when you do iterative, cache previous results, and because the changes are less frequent higher up the hierarchy, any name resolution at the top level hierarchy can cache for longer. Okay, so all cache data will have an expiration time. Okay, so the expiration time you associate with lookups higher up the hierarchy will be longer. Lower down, because there are frequent changes, you might say expire in 30 seconds. But if you resolve something at .com, you might keep that for days. So that doesn't change very frequently at all. Okay, so the expiration times are carefully matched to what level of the hierarchy you're caching data from. Higher up, you can cache for longer because there are fewer changes. So less likely your data you have cached is out of date for any particular reason. Okay. Right. So now I'm going to show you some advanced features you can actually use in case of DNS. Okay, so one is actually already shown on this slide, but I'll show you an example as well. So if you look at this machine here, which is star.ch.vu.nl, if you look carefully, you'll see that the same machine actually has two A records. Okay, it has actually two IP addresses. Okay, so you can have scenarios. An alias is where one machine has two names. Here, CNAME is a scenario where this machine actually has a second name. Here's an opposite case where one machine actually has two IP addresses that it's answering to. Okay. So this kind of feature can be used for things like clustered web servers, where you have a website that is replicated onto multiple machines. Okay, and then if you type the name of the machine, it will result to multiple addresses, and any IP address can actually give you the service you are looking for. Okay, so let me show you a specific example. Okay, so let us resolve the example I started with, which is CNN.com. That's interesting. Show us some replica doc. So let's see if this has anything better for us. Okay, so these are all resolving to. Okay, so here is an example where. So this actually is going to show us two different things. So I resolved Intel.com. Yeah, you will see that in the end it gave me two IP addresses, and my browser can actually connect to either of those two, and then you will get the information from either of those. So this is used in replicated websites. Okay, so, and then what happens is when different browsers try to resolve it, you will send these entries in different orders, okay, because typically the browser will pick the first entry and connect to it. So as another browser, you might get these two in two opposite orders. So some machines connect to this IP address, some machines connect to that IP address, so the load gets balanced. Okay, so DNS is also used for load balancing for clustered web servers, and this is why one machine has multiple IP addresses. Okay, Now the second thing which is also interesting in this case is you see that when I resolved this, it actually gave me a bunch of different information. But what is more important is if we actually look at this IP address, okay, you will see it's 192.189.138.83. And if I try to actually figure out what that is, so I'm just trying to resolve the dot one. So you will actually see that IP address is actually a UMass IP address. Okay, and in fact you can see this if I actually do 183. You will see it basically says some vendor.umass.edu. Okay, so you can ask why is the Intel website actually hosted on a UMass machine. Okay, that's what this is telling us. So the reason is this is actually hosted on a content distribution network. The CDN has actually put caches in multiple organizations. In particular, this is part of the Akamai CDN, which is a commercial content distribution provider. So they have gone and put caches in every organization. Okay? And in particular, Intel's web pages are cached on the CDN provider. So you don't actually have to go to the real Intel website, the server, to get the page. You can actually go to a local cache, which happens in this case to be a machine in the UMass domain. Okay. Furthermore, if you go and do this name resolution from, let's say, home, it will result to some other cache. Every time it is sending you to the nearest cache, so you can get the fastest response time. So this is an example of DNS using intelligence of who is making the DNS request and returning different responses based on where is the nearest server to service that request. In this case, the nearest server is a cache that just happens to be actually located within this organization. Okay, so you can use DNS for all of this more advanced web-based optimizations as well. We will come back to content distribution networks later, but this is just something that is interesting from a DNS perspective. Okay, so what your browser will do is actually connect to that machine, which just happens to be a local machine in the LAN here, and get the web pages from there. Okay, so your response time will be much lower than if you had to go outside to a different web server. Okay, any questions on this? Okay, so that's all I have to say about DNS. Just to give you a flavor of other kinds of naming services, I'll talk about another one called X.500. Okay. So DNS is a naming service that provides you very simple lookups. You specify machine names, it gives you IP address. Okay. That's the only kind of lookup that supports. It's a pure key value lookup. You cannot do any more advanced lookups like queries. Okay. So for example, if you wanted to look up, let's say you have phone directory yellow pages. Okay. In phone directory also you have a name and you can get a phone number. But a yellow pages allows you to do more general lookup, saying I want to find a plumber. I don't know the name of the plumber, but I just want to find all entries that match type plumber. Okay, and then it will basically add some more general query that says show me all entries that match this attribute. Okay? And then a list of matching entries will be shown. You cannot do that kind of lookup using DNS. Okay? But there are other directory services, in particular X.500 and LDAP that I'll show on the next slide, that allow you to do more general purpose queries. You can essentially ask for any matching attribute, and then it will show you all the entries with that attribute. So you don't have to give a full name and try to find the lookup. Okay. So X.500 was a standard that was developed to perform this more advanced kinds of directory services. What is now used more widely is a more specialized form of X.500, which is called LDAP, or Lightweight Directory Access Protocol. Okay, this allows us, so this is LDAP in X.500 that runs on TCP/IP with some restrictions, but it is essentially the same concept. Okay? And this is widely used in most organizations. You can use OpenLDAP or Windows Active Directory. Any of these services that most operating systems provide are an example of an LDAP directory, okay, which allow you to do. So usernames and passwords are stored in there. Okay, so if you are trying to log in and you specify username, password, your machine will contact a directory service, which might typically be OpenLDAP or Active Directory, say this user is trying to log in with this password, is it correct? Okay, so then you'll authenticate against an LDAP protocol. But there are many other kinds of resources that are stored in these kinds of directories as well. Okay. The UMass People Finder, okay, is an example of an LDAP implementation. Okay, I presume you know what People Finder is, right? Okay, if you go to the UMass webpage, at the very top you will find People Finder, and you can go type someone's name and it will tell you their phone number and their address, their office information and so on. That's an LDAP lookup. Okay, you can do partial lookup. You can say find me all names that have this last name or just some part of a last name, and it will allow you to do that kind of lookup. Okay, so I can show you an example of, you can go to the UMass web page and do this, but I have an LDAP client that allows me to do this, assuming it works. Okay, so I basically just typed two letters SH. Okay, it showed me all last names that start with SH. This is an example of doing arbitrary lookups. Right? So I did not even specify someone's full name. So it's going. So essentially, allowing me to do wildcard queries. Okay, and you can essentially then I'm just going to type my last name, and you will see that it gave 4 names, 4 people who have the same last name as I do that are all part of UMass. Okay? And you will find that their phone number, emails, whatever is recorded in the UMass directory, all that information will show up as well. Yes, question?
Isn't this used for contact storage in Outlook? For like contact sync and storage, I think like that.
Okay. Question is this used for contact storage? So this is a directory service that can store people's contact information as well. Okay? Outlook itself uses things like Active Directory. Yes, because Active Directory is the Windows implementation of LDAP. Okay, so if Outlook needs to store your contacts, typically if it's stored on a network server, it will use Active Directory. If you just have a local implementation, it may store it on a file. Okay, so it depends on what version of, so if you use Exchange, for example, it will use Active Directory. If you just have local contacts, it may not. Okay, so here is the LDAP. LDAP is also a hierarchical naming protocol. It has hierarchical namespace. So this is how you create records in it. So you'll say country is Netherlands, organization, which is a O record, is a university, organization use, so it's a department is math and computer science. You will have name server, host name servers, and so on. So you can also use LDAP to do local IP address resolution. Okay, DNS will then first use your local directory to look up local names. If not, it will go to DNS to then resolve the rest of the names and so on. So it's a very general purpose protocol, a directory protocol. Can do all kinds of directory lookup, username, passwords, people's phone numbers, IP addresses. You can store names of printers in there and whatnot. So there are many different uses for these kinds of protocols. Any questions here? If not, I move on to the very last slide here, which is basically how do you provide naming for mobile devices. Okay, so what is shown in this example is a case where you have a user with a mobile device. Okay, the user just goes from one location to another. Okay, now, if you wanted to have a fixed IP address for the user, okay, the user is in UMass domain, you give it a UMass IP address. But if I go somewhere else, okay, that IP address may not be valid anymore because that's a UMass IP address. If you try to connect to that IP address, all the packets actually come here, but the user has gone somewhere else. Okay, so when your mobile devices, naming is a particularly challenging problem because most of the naming services that we have seen associate names within an organization and a particular location. Okay? When the location of the device changes over time, okay, the names will also have to change, and that makes things more clunky. Okay, so for example, if you just take your laptop and you go home and you connect to your own Wi-Fi network, you get a different IP address altogether. It's very different from the IP address you had before. If there are clients connected to your machine, all those connections will break because your IP address has changed. Okay? If you don't want that to happen, then you have to use a different kind of naming system that allows you to connect to machines regardless of IP address changes. Okay? So there is a concept of what is called mobile IP, which keeps your IP address fixed regardless of where you go. Okay? And the way it is going to handle it is essentially you have a home location for your IP address. Okay. Anytime someone wants to connect to you, they may basically connect to your home location, but regardless of where you go, you essentially use a forwarding address. Okay, so this is the same thing that happens if you actually move to a different apartment. You can keep a forwarding address with the post office. Right? So if somebody sends you a letter to your old address, the post office has a record saying send it to this new address instead. Okay? The same thing is done by mobile IP, where your IP address will not change regardless of where you go. You have a mobile IP address that remains fixed. We can always be contacted on that same IP address, independent of where you go. Okay? And the way a TCP/IP will make that work is you will have a home location, and that home location will forward you packets regardless of where you are at the current time. Yeah, so that is essentially, so you will essentially have tunneling and so on. Now this is not widely used in practice yet, although with all the explosion of mobile devices, these kinds of protocols eventually will become a lot more useful. Otherwise, every time you change locations, your IP address might also change underneath, and then that makes it much harder to keep connections alive, keep applications going, and so on. Okay, so the takeaway is, when you use naming for devices, mobile devices in large distributed systems, things like DNS or directory protocol don't work very well, because they are designed assuming the nodes are actually associated with a given location and a given organization, which is, that assumption is not true anymore when you have mobility. Okay, so handling naming in the context of mobility is still an open research problem. There are many researchers who are still developing new naming systems that actually work with mobile users and mobile devices, and mobile IP was just one of many different approaches that have been proposed. Okay, so that is something you may want to keep in mind from a naming perspective. It's not that all the problems have been solved. There are still interesting problems from just designing naming systems for mobile users. Okay, this question.
How does this compare to dynamic DNS system?
So the question is, how does this compare to a dynamic DNS system? So so let me explain quickly what dynamic DNS system is. Dynamic DNS system is an approach where you use DNS with a fixed name, but the underlying IP address mapping can be changed as frequently as you want. Okay, so this is often used if you are using DHCP based system, where every time you do DHCP, your IP address has changed. If you want to still allow users to connect to you, you advertise a name which is fixed, but the name to IP address mapping can be changed in the DNS. Okay? So dynamic DNS just says every time my IP address changes, I re-register with the DNS at the managerial level and say, if you want to connect to my machine XYZ, here is the new IP address. So reconnect using that IP address. Okay? So that will work so long as you are willing to let your connections break and reconnect. Because if your IP address changed, all the connections to your old IP address will no longer be valid. They will actually break. So it is not transparent to the application. But across user sessions and across connections, it works just fine. Because if you want to set up a new connection, that will work just fine. If you have an existing connection, dynamic DNS will not help, because those connections will be. Mobile IP is allowing you to do both of those things. Okay, it will not only keep your connection alive, but also it will allow you to address it with the same thing. Okay, so it's a different, slightly different approach to addressing some similar problems.
So I think I used to use dynamic DNS to host a server at home using my internet. So I think that's the thing, right? Like when clients could disconnect to my server.
If you use dynamic DNS, if your IP address changes, you will re-register. The old connections to the old address will no longer be valid. You have to reconnect. So if you can tolerate that, that's a fine approach, where you just change the mapping and you re-advertise the mapping, and that's it. Right? But it's not transparent to network changes.
Will the mobile IP be like supported over the current infrastructure or the current network hardware?
Okay. Question is, can mobile IP supported over current infrastructure? There are proposals that say, how do you implement this in public internet? Okay, these do require changes, which is why some of these things haven't happened. Any protocol change is hard. Okay, no different from going from IPv4 to IPv6 address. That also needs changes. Okay, so there are many of these are still not completely implemented or partially implemented. But yes, it was developed in the context of IP. Question? All right. So let us stop here today. We will continue again on Monday with the, actually we finished naming. It was a short topic, is actually one chapter in the book, but we just went through it quickly. Next time we'll start a new topic. Where would it come from?
Your place of scholarship.
Usually I've done this in the past, I don't think this time I'm-
It is showing me that it's available one recommendation on it. I have given your CS mail ID, the official mail.
Can you resend it?
I'll try.
Usually I get a mail, but just a bigger,
So it's just like a string. It's just like
it's just a bigger address because the current address space is limited. So they just make the address
so the
bigger.
value is actually like meaningless sort of code. It's just like no value storage, which just returns.
Just a bigger numeric address. IPv4 is a numeric address. Because they ran out of addresses, they just made it bigger.